Okay, now that we've talked about the basics of factory methods, let's talk about the next set of advanced features. And this is really the heart of the whole thing. These are the so-called completion stage methods that are used to chain together actions that perform async result processing in composition. This is the bulk of the stuff. As you can see from the pie chart here, it's like, I don't know, about 2/3 of the methods are so-called completion stage methods. So what the heck is a completion stage method, and what is it used for? Well, as the title implies, completion stage methods are used to chain actions together. So a completable future can serve as a completion stage for async result processing. I strongly recommend you take a look at this link and read about completion stage, because it really gives you a lot of good explanations that also apply to completable futures. In fact, there's honestly better explanations in completion stage documentation than there is in the completable futures documentation, which is kind of funny. So here's what you do. An action can be performed on the result of a completed async call. And this is where we start getting into the advanced features that don't come out of the box with regular old futures or the basic features of completable futures. I'll show you this example in more detail later. This is just more big fraction stuff. But essentially what we're doing here is we're going to run the reduction operation. Here's the reduction operation. So we go ahead and we make ourselves a big fraction that's unreduced. So it's unreduced. We then make a lambda supplier lambda, that will reduce this unreduced fraction. We then run the lambda via supply async, the factor method we just talked about. That'll run in the background, so that's chunking away, doing stuff in the background. And then we go ahead and once it's done being reduced, we then go ahead and apply this method reference in order to convert it from an improper fraction to a mixed fraction. And leaving aside all the details of what's going on, the main point here is that this code here, this action, big fraction, : : 2 mixed string, which is a method reference, that action is run after this reduction completes. So that's what thenApply is doing. And I'll talk more about thenApply in a second. But the point here is that this is done after that is finished. As you'll see here, once you have this ability to perform operations when other things finish, you can then chain them together. Not unlike the streams stuff that we talked about, right? So streams, and we talked about how streams, you kind of chain things together in a fluent model. This is much the same thing. The main difference is that what's happening here is you're chaining together actions that get called when the previous stage completes, right? So here, after we've reduced the big fraction and we've converted it to a mixed string, then we go ahead and print it out, right? So this is a chain of operations. And each of these methods here, these are called completion stage methods. These two, thenApply and thenAcceptor completion stage methods. Supply async is a factory method. Each of these things registers a lambda action to apply when the previous stage is done. So what's happening there is that this is being deferred, right? In other words, we're taking these actions and we're saying, don't run them yet. But when this thing happens, when the results are done, then run the action. So this invocation of the lambda action is deferred until the previous stage or the previous future completes. So these things are not run immediately. They're deferred and they're run when it's their time to run. And as you can see here, the way it works is that these actions are only called after the previous stage completes. So it's kind of like a little pipeline or a chain of these things. All right, any questions about that? What's weird about this at first glance is you think these methods are being called in order, and they're not. They are being called in order, but they're not being called immediately in order. They're being called when the method ahead of them finishes its computation and the future is completed. Then the action of the next stage is called to do whatever that stage is supposed to do. So why the heck are we even doing all this stuff, right? What's the big picture view? The big picture view here is we're trying to not block threads until you absolutely have to. You want to let the thing all run asynchronously until you really, 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 really need to get the result. And that's why in your programming assignment, you'll see that you only hit block for the very last thing. When you're joining on the results of all the asynchronous crawling, one place you should call join. Everything else is just running asynchronously. And the only reason we have to do this is because our little program has got to actually eventually give the result to the user, right? You have to finally present the result on the display. And once I get the projector working, you'll see how cool it looks. If you're writing a server, you probably would never have to call join because it's just going to keep running till it's finished and it'll give the result back. So you're not going to have to join. So the best way to think about completion stages, or at least the way I like to think about completion stages, is kind of like juggling, right? So anybody here juggle? How many jugglers? I've never figured it out. I've tried it a couple times. I always end up dropping whatever I'm trying to do. The time I dropped the flaming chainsaw on my foot, that's about the time I decided juggling really wasn't for me. But the idea here is that with juggling, as you know, if you've ever seen people juggle, the idea is to keep as many balls in the air as possible. And you do, of course, have to eventually touch the ball, but you only do it long enough to move it from one hand to the next to throw it up again. So it's like, this kind of thing. That's probably why I'm a bad juggler. I never figured out the motion. But the same thing is true with completable futures. The idea is to have things running, usually asynchronously, and only grab their results long enough to get them going asynchronously again. Right? So that's kind of the way to think about what's happening here. And the win is to really block for as little as possible. And we'll talk later about why you do that. Okay, so there's a number of different ways to group these completion stage methods. And they're typically grouped by how they wait for the previous stages to be finished, to be triggered. So one group of methods are triggered when a single previous stage completes. As you can see, there are four main methods here: thenApply, thenCompose, thenAccept, and thenRun. And for our purposes, the key things are thenApply and thenCompose. We'll also look at thenAccept, but thenApply and thenCompose are really important. And as you can see, there's a bunch of different behaviors. I'll talk about this stuff in a second. This is just the summary of all the different things and how they work. Now, you'll also notice for each of these things, there's an async version of all of them. And what the async variants do is they run the computation in the common fork join pool. So all the methods that say blop blop async, it takes the function and the work and it says, run this thing in the default common thread pool. By default, if you do not do this, then typically the next computation will run in the same thread as the thread that was just running the previous computation. Although that doesn't always turn out to be the case. It's a little mysterious, but that's the way to think about it, is to think about async will run things in some other thread in the common pool, and not using async means that whoever just finished running it in the background will most likely run the action in that background thread. That's not always the case, but that's usually how it works. So that's one set of things. The previous stage completes. These are the methods that get run. Then there's also a set of methods that run if both of two previous stages complete. So we could essentially call that an AND. That's bringing two things together, right? And we'll talk about some of the stuff here in a second. Then combine, I believe we'll look at. And then the third and final grouping of things are you can have a completion stage that completes after either of the two previous stages complete. So it's either or, right? So, think about over here, it's kind of like stream coming together, two things being joined, but just two of them. Over here, it's kind of like the movie The Matrix. You have the red pill or the blue pill, right? You can pick one. You can't pick both. So that's the or alternative. So that's just kind of the high-level view. Now let's take a look and see how these things actually get used. And I think we have enough time to cover a lot of this stuff. So remember, the first discussion here are methods that complete when a single previous stage completes. And the first one we're going to look at is called thenApply, and you'll need to know how to use thenApply. ThenApply is a useful method. It's simple, but it's useful. So this applies a function, which is passed as a parameter. This is the function action. It applies the function action to the result of the previous stage. And it returns a completable future that contains the results of applying the function. So it's going to return a completable future to whatever the function's return value is. So you can see here that the function returns a u, and that's what comes back from this. So the function will return a u, and you'll get back a completable future to u as a result of thenApply. Here's a very simple example. You typically use thenApply for synchronous functions that return a value, not a future. That's going to become really, really important in assignment 3A. And I guarantee you, you will spend a lot of time scratching your chin and trying to figure out this stuff. So let me talk about it quickly, and we'll go back if you have more questions. So this is what I showed you before. Supply async will do the reduction of the big fraction in a background thread in the pool. And then when that is finished, thenApply will have that result turned into a mixed string. And toMixedString is a synchronous function. It returns a value. It returns a string, right? Not a future to a string. It returns a string. And thenApply will return a completable future to this string. That's just the way it works. Now, you might ask, why the heck does it even bother doing that? Because this thing is going to, since it's synchronous, we've got the result pretty fast, but that's just the way that the API works. So thenApply is typically used for things that return values, and then it wraps a completable future around it. There's a problem, there's a limitation with thenApply, and to solve that limitation, we have another method called thenCompose. And thenCompose is a bit more powerful, and we'll talk about how it works. So we have thenCompose. This applies a function action to the result of a previous stage. So far it sounds pretty much like thenApply. However, what it does is it returns a future to the result of the function directly, rather than returning a nested future. And you'll see in a second why we have this method. It's really cool. It's actually quite a bit, well, I'll tell you what it's like. It's basically similar to flat map on a stream or an optional. If you remember what flat map did, flat map takes a stream of streams and it flattens it into a single stream, or it takes a stream of lists and turns it into a stream, or whatever it does, right? So flat map is used to flatten things. You know, again, there's lots of examples. It's kind of like merging lanes in a big highway. So you kind of merge them together so there's one lane. And so here's a visualization of this. It's a little bit hard to see, but it's cool if you can see it. So when you use thenCompose, you can have, you know, completable futures, and you can add things together or whatnot, and you get back a single completable future as the result. What you do not get back, which is what you would get back if you used thenApply, is you do not get back a completable future to a completable future, right? If you look really carefully, these are nested table tent numbers, right? So they're kind of stacked on top of each other. So you do not get back a stack of these things. You just get back one of them. And that's what thenCompose does. You will need to really understand thenCompose to do the next assignment, because the whole thing kind of, the hardest part of the assignment is thenCompose for sure, knowing where to use it. So here's an example of where you might use thenCompose. So what we're going to do here is we're going to, and actually this comes from that example 8 thing I've been showing you as my running example. You can see this in there. So what we do, I abbreviated big fraction because it was getting too big and it was running off the slide. So BF is big fraction. So what we're going to do is we're going to have an asynchronous reduction of an unreduced fraction. So we're going to get back, you know, we're going to have this lambda expression will run something in the background and return a completable future. And then down here, we're going to have the thenCompose method. So when let's see, I think this should probably say reduced. Shouldn't say unreduced, it should say reduced. Oh, I take it back. This is perfectly fine, everything's right. So notice what we're doing here. We're saying then supply async, reduce the unreduced lambda expression, and that returns a completable future to a big fraction that will be reduced when the future completes. Then we compose this. notice how this is chained together. Supply sync followed by thenCompose. This is just what's called back after this guy is finished. So after this stage completes, we have a reduced fraction, and we're going to take that reduced fraction, and then running in the background, we're going to multiply it by some other fraction. So, and conceivably, if the fractions are big enough, multiply might take a while, all right? So it could take a long time to run. And so notice that supply async returns a completable future, because it's an asynchronous call. Well, we don't want to end up with this. We don't want to end up with a completable future to a completable future, but that's what we would get if we did thenApply. If we use thenApply, thenApply simply takes whatever its result is and wraps a completable future around it. Well, if its result is a completable future, thenApply will give you a completable future to a completable future, which you can certainly do, but it gets ugly and unwieldy in just no time at all. So a much better thing to use is thenCompose, because that will reach into the completable future result, get the result, and then wrap a future around that. So it's like flat map. It flattens it out. So supply async will return a completable future, and then thenCompose will reach inside, get its result, and then make a completable future for that thing. Okay, so this is unwieldy. We've got to use this. Now it turns out, and this is really important for your next assignment, there are some wacky situations where you actually have to use thenCompose on the identity function in order to be able to, again, avoid having to call join. So here's an example. We are going to want to get a completable future to an integer for some reason, and we're going to call supply async, and supply async is going to return a completable future, and we just want to get that single completable future as the result. Again, we don't want completable future, completable future. Well, one way to do this would have been to say, supply async, return completable future, dot join. We could have said dot join here, but that would have required blocking, and we don't want to block, because blocking is bad. So instead, what we're going to do is we're going to say thenCompose, but we're not going to do anything to the result. We're just going to get the underlying completable future and unnest it. And so in that case, you say thenCompose function identity. And the function identity will end up just sort of being a no-op whose purpose is just to make sure we don't end up with a completable future to a completable future. Yes, Caleb? Sorry, ask the question again. Yeah. Oh, yeah. Okay, so let me see if I can restate the question. So why are we not just saying return completable future? Because if we just said return completable future, it wouldn't run in the background. Because notice what supply async is doing is running this thing in the background. Whereas this thing, normally, let's say if we peeked inside return completable future, it was just some function doing something or other. Well, it could be doing a variety of things. And you'll actually see in your assignment an example. So in your programming assignment, you're going to have a function that's called something like crawl hyperlinks on page. And crawl hyperlinks on page is going to return a completable future to an integer result. And we want crawl hyperlinks on page to run asynchronously. So we have to call it from within supply async. So what would happen if we didn't call it in supply async, it would block, which we don't want. When we call it in supply async, it no longer blocks, but now we get back a completable future to a completable future, which is one too many completable futures because they're nested. So we use thenCompose function identity to strip out the extra function, extra future, kind of reach inside, pull it out, and then flatten it and give it back as a single completable future. So it's this wacky idiom, but the reason for using it is to avoid having to call join while still allowing things to run correctly in the background. So as I was saying, this is an idiom. You see it used not infrequently, and it's usually used to flatten the return value to a single completable future rather than nested futures. Again, you'll need to use that. You will get to a point when you're doing assignment 3A, and you'll be like, how the heck am I going to get from what I'm getting back here to a completable future? And when you reach that point, remember this idiom, because it'll save you. Another completion stage method that's triggered by the completion of the previous stage is called thenExcept. This basically applies a consumer action to handle the results of a previous stage. And the action behaves something like a callback in the classic sense of the word callback. And that's because it's going to have a side effect as opposed to returning a value back through a completable future. Notice how thenExcept returns a void, completable future to void. And something went wrong with my font, switched. So it returns a future to void. That just means that there's no return value that comes back. So what that's saying is we're going to have a side effect here. And this is often used at the end of a chain of completion stages to call a method that has some kind of side effect. So you can see here we've got the same example we did before. We do the reduction in a background thread in the pool. When that's finished, we convert the fraction to a mixed string. When that's done, we then accept the result and we call print line or whatever, and that has the side effect of printing the result. So it doesn't return a value, it just has a side effect. So thenApply returns a string future that thenExcept prints when it completes. So it has a side effect to do that. Okay, so those are all the things, those are the key methods that are used when a single stage completes. Let's talk about combining stuff. This is also, of course, going to be very important for your next assignment. So for your next assignment, just make sure I'm not running behind on time. All right, we're fine. So for the next assignment, one of the things you have to do is combine the results. So that's done by thenCombine, among other things. And you can think of thenCombine as basically merging the results. So thenCombine applies a by-function action, this is a by function, to the results of both previous stages when they complete. That's the key thing, when they complete. This returns a future containing the results of the function that's applied. And you can think of this as basically performing a reduction. So it's like you got two, don't get confused with streams, these are not Java streams, but two flows of things coming together, and we end up putting them into one. So it's used to join two paths of execution. Here's an example. Let's say we have two completable futures, comp F1, comp F2. They both go and do some computation. This one's going to multiply two big fractions. This is going to divide two big fractions. And then we're going to take the results of both of those things when they're done, and we're going to add them together. So just showing you can do a bunch of stuff, and then you can wait for those things to finish, and then you can apply yet another operation, which in this case is to combine the results. Okay, so that's and, right? That's both of them. And then the last thing we'll kind of cover here, and then we should pretty much be done, is what you want to do when something's triggered by the completion of either of two stages, right? So this is now back to the matrix, you know, red pill, blue pill, whatnot. You do either of them. And this basically applies a consumer action that handles the results of either previous stage, whichever one finishes first. And this returns a future to void, so it doesn't actually return a value. I mean, it just returns that it finishes. And it's often used at the end of a chain of completion stages. So here's an example. I think I mentioned this to you before. This is a really crazy example. This is what happens when you have so many cores, you just can't figure out what to do with them all. And you just want to do stuff that is almost, you know, extravagant, right? It's embarrassing how much parallelism you have. So what we're going to do here is we're going to have a list, and we're going to quick sort it, and we're going to merge sort it. And as you know, the behavior of these sorting algorithms is often a function of the characteristics of the input, right? So quick sort, for example, or certain things work really well if something's almost already sorted. Like insertion sort works really well if something's almost sorted, whereas quick sort might not. And merge sort might work better, or whatever, right? The point is that they're trade-offs. So rather than try to figure that out, we just run them both. So we run them both in the background, and then we accept which either result comes back first. So it's either quick sort or merge sort, we don't care. We get the results back, and then we take the result, and then we go ahead and print it out. So that's an example of leveraging all the cores at our disposal to just do computation, and whoever finishes first, you take their result. Okay, so that is the end of the